I guess we still have one more minute of freedom. Before we officially start class, I suppose I can bring up the fact that if you found a free version of the text, I got an email or two, and I imagine that means more of you are in the same situation. Chapter 22, in the latest edition of the text, you would expect the chapter numbers to stay the same, but they didn't. So you might have, did anybody read about thermodynamics by accident? Awesome. That's what I was curious late this morning, actually. Like, well, okay, so how easy is it to find a PDF of an earlier version of the text? And so I did that, and I was like, oh, great. Wait a minute. That says something about thermodynamics, maybe heat engines, I don't remember what. And so I went back and I checked the current, and of course that was, I guess, in the current edition, chapter 21. So I don't know, somewhere they changed the chapter numbers. So put your hands up again if you read about thermo. There's 2, 3 of you. Yeah, I was expecting as much, and that would make it hard to take a quiz on electromagnetic phenomena or electric phenomena. So, okay, a few things. The quiz. How about I do this? Now, I guess there are multiple things that I have to discuss about course format that probably could have happened yesterday or Monday before we got into things. Number one, you guys have come from different sections of mechanics, the first semester course, some of which used this text, some of which didn't. And that presents a problem because some of you guys, I guess, have access to the text already because it's ongoing from last semester. Is that actually true, or was it at the end of the semester was your access just cut off?
Some bought 2-year subscriptions, some people bought 1 semester.
Did you say 2-year or 2 semester?
2-year.
2-year.
Yeah.
Interesting. Was that a lot more expensive than?
To some extent.
Okay. And so does nobody get it through inclusive access? Do you know what that is? I guess the university has some yeah, so some of your courses, I think you don't have to pay anything for the text, right? And I don't know why or how.
You still end up paying a course fee in your registration.
You somehow, so it's a hidden fee?
Yeah.
I see. So you pay it whether you like it or not. It's free, like the free phone that you get when you sign up for the plan. Nice. Well, I guess whether you did or didn't, I think what must be the case then is that they didn't charge a course fee for this course, so that if we use the book, you have to pay additionally now, and if you don't use the book, then we don't. And what I was going to suggest is that whatever version you have access to, we can use it, but the trouble is that the homework problems aren't going to be the same, and certainly the computerized homework homework system doesn't come along with a PDF download that you find of the 2 editions earlier version of the text. So I was leaning toward, and I like it that way better anyway, to do reading quizzes, which I think we can make quick and easy, done on Canvas. So just to keep you guys up to material, reading it before we start lecture on any new topic, we'll do those on Canvas. And then the homework, I'll give you homework sets, and we'll make sure that everybody has the same sets, so not just by number, but here's the problems to solve. And then you'll go over those and learn how to do them, and we'll take homework quizzes, like 2 problems every second week roughly will be the way that we keep homework points. And the breakdown will be, the reading quizzes will be 10 pointers each, and we'll make 25 out of the homework quizzes, and that'll still, if you look at the way the points are laid out, I think right now I think the points are actually right in the syllabus as it is, but if they're not, I'll fix that after class. And praise the Lord, I found a cool tool from my end. Canvas I've never been super fond of because it's a pain in the butt to deal with. Like a lot of things that should be easy aren't, and you can't do them in batches. And I found a Python tool that has a Canvas API that then I don't have to deal with Canvas. I can just write Python code and it'll do, change 10 things at once for me at the push of a button and a little writing of code, and I'd much rather do that with my time. So I'll make sure all that's fixed. The immediate concern is we were going to have a reading quiz, but since it's not on thermodynamics, how about I make that after class? I'll stick it on Canvas, and it'll be due by like midnight. Do you want to do that? Do you have a question?
No.
Okay. Okay, yes.
Would you be able to post a PDF of the text?
I will. I'll post the one that I found. Assuming that's not a copyright violation. I guess if it's already freely and easily. I'll give you the Google search that I used to find the source, just in case. Maybe I'll have a conversation. Maybe I shouldn't even ask. I'll just give you I'll give you a Google search term you can use, and make sure. I don't think it's a copyright violation. As much money as we give the publisher, as a university, I think it's okay. It's an interesting thought because copyrights last 99 years, if I'm not mistaken, and pretty sure it's newer than that. But I don't know if there's some weird agreement where new versions of a text come out and the publisher themselves are like, yeah, you can have the old one because it's no longer valid. And maybe they voluntarily, I no idea. We'll just not have that conversation and not ask Gemini what it thinks about that. Good. So I figured that out. Did you guys see the top hat code, Hayden 934, and take care of that? I didn't bring my USB-C to HDMI converter, so I can't show you my screen, but that's no problem because we're going to do stuff on the dry erase. But that's why the number's written instead of seeing it on here. So for all but a few of you, what you read about was electric charge, electric fields, Coulomb's law, continuous distributions of charge and how to find the field near them. And we're going to spend essentially probably all of this week and next week going over those types of problems. A few things. First thing to be said is this. If you looked at the convention that the book used for, yes?
If you need a converter, what happens?
Do you what?
If you need a converter.
Oh, I don't. If I find the need, the only part that I might want to use it for is I have a cut and paste example from the text that I was going to do differently, and maybe at that point, just because who knows what problem number it is in a different version, I'll just show it to you. But either way, you have access to it afterwards. But the convention that the book uses for Coulomb's law in terms of the subscripts. You remember how we wrote F12? So the idea was call this charge 1. I'll put charge 2 someplace else. And of course, the size has no relevance if we're talking about charges, but I'm making them look different because I'm going to attribute different amounts of charge to them. Maybe I should do it the other way. I'm going to call this 2 and this one 1. So the little guy is going to be represented as less charged. But you have to have a coordinate origin in order to define a position vector, right? So I'm drawing it someplace. And here is the convention. By the way, that's a cursive R if it's not clear. Position vector 1, position vector 2. Anybody happen to remember when we wrote out the force? First of all, how do I interpret the sequence, the two subscripts on F, based on our discussions last time? When I write F12, what am I meaning? Yes?
The first number is like the one that it's being acted on.
Yeah, that's right. So the easy way to think is this is on, by, or due to, right? So, and if you write it out thinking along those terms, what's the form of the equation then? There's a bunch of 1-2s in there. Starts off with what? Constant. You remember the k part? And then what else does it depend on? Q1, Q2, Q1, Q2, and then what was up here? Well, it wasn't Q's, it was all about where they are, right? So what was it in the bracket on? Yeah, it's R1 minus R2, and the exact same thing, this quantity, in the denominator, but what else do we have to do to it? Magnitude and what power? It is cubed. And we had that discussion where while it looks like an inverse cube law, it's not. It's an inverse square law. If you compare this to what the book, and this is referred to as Coulomb's law, we're going to find that Coulomb's law really isn't a fundamental principle. It's a consequence of a more powerful fundamental principle, which is Gauss's law, that we're going to get to in the next chapter. But for right now, what we had was similarity with gravity, in the sense that if you replaced charges here with masses, m1, m2, and instead of this constant k, replace it with a gravitation constant, big G, then we have, and with one other thing, remember the minus sign, it leads to Newton's universal law of gravitation. And so for right now, first thing I wanted to say is this convention, the book does it the other way. But it is so sparse with the rigorous use of vectors that it almost doesn't matter the way the book does it, because they aren't as rigorous with the math as they should be. And that being said, if you look at pretty much every other text that is rigorous with the math, that all the higher level that you'll find, they do it my way. And so what we're going to do, we're going to do it my way. And it'll make more sense. One of the reasons it makes more sense, you'll see, falls automatically out of the math when we start thinking about not one thing affecting this guy, but many things affecting this one charge, or a continuum of things affecting this one charge. It would hurt your mind to do it the other way, because there's one thing that I'm focused on, like what is this thing experiencing due to everything else in the world and the environment. And anyway, it makes more sense, and it's, I guess, rather unfortunate that the author of the book didn't think so, or didn't do it that way. But if you look at this and then you just decide, hey, vector version of Coulomb's law, and you hit enter on YouTube, they're all going to be this convention. So I think in terms of cross-referencing and finding other materials, we'll be much better off doing it this way. And it works so beautifully in the pictures, because then I think about the vector, the charge, all of these, and the force. If these are both positive, you can imagine that I draw this vector and everything. This is what we should be thinking of as this picture, so that the 2,1 acts on charge 2 at position 2, and the 1,2 acts on charge 1 at position 1, and all the first subscripts match. Of course, there isn't a second subscript here, but this guy, this guy, this guy match, and ditto on the other charge. Does that make sense so far? Okay, so since we discussed that already, maybe I will use your USB-C to HDMI just to show you an example problem that's in the text. I guess that's as far as it goes. I have to move this. Thank you. So, such a show just for one problem. So this is from the possibly copyright infringed version online. In that book, chapter 23, example problem 2, and what they have is a picture of, as you can see, 3 charges. It says, consider 3-point charges located at the corners of a right triangle as shown. Q1 equals Q3, is that a 3? Yes, equals 5 microcoulombs. And Q2 is negative 2 microcoulombs. They give you a distance A is 10 centimeters. Find the resultant force exerted on Q3. You see that? So they want to find out what's happening to the charge in the top right corner. I don't know how easy it is to read the subscripts from where you're sitting. So 2 charges are really sitting along the y-axis, one of them at the origin, one of them someplace up on the y-axis. We want to figure out what's happening to the one on the top right, the orange one. And if you look at the way the book goes about it, really, they start off with use equation 23 to find the magnitude of the force, find the magnitude of the force between 2 and 3 and between 1 and 3, and then they go through this trig, like, okay, so it's like draw the vector, find the angles, and manually do it, and that, first of all, there's extra thinking involved. It's like, oh, I have to recognize manually, sort of, that the charges, which are labeled 2 and 3, which is the blue one and the top right one, are opposite in charge, so that I should make that magnitude, of the vector directed leftward, so it's attractive. And then the other two, I look at them and I have to manually think again, okay, plus, plus, so it's repulsive, and the force that they're labeling F13 is going rightward and upward, so that they, the two orange are repelled from each other. But what's nice is if the math did all that thinking for you, meaning, what if I just didn't want to even have to look and think about, wait, opposite signs, attractive, so I need to put it this way and then figure out the angles. What if you just wanted to put in a coordinate and have the equation spit out the right answer? Enter this equation. That's all you have to do. And the idea is this. So how would I take the same information? Let me write out, the numbers they gave us. Q1, so I can use that as, what was Q1 again? Q1 and 3 are both 5 microcoulombs. So Q1 equals Q3. 3, let me make it legible. 5 microcoulombs. By the way, unit of charge, Mr. Coulomb, Frenchman, got the unit of charge named after himself. And then Q2 is -2. So Q2 equals -2 microcoulombs. And the picture, not that picture, is this. We have the charges labeled. Sorry, that was backwards. Let me try that again. So this is, bottom left is 1, top left is 2, right? I can't see it from either screen. I think it's this way, right? Did I do that right? Q2 and Q, yes. Okay, so these are the 3 charges, location-wise. And magnitude, or the actual, sign and magnitudes of charges are given. So how do we do this? Well, think about this. We need, if I want to use this equation, I need to know where the charges are. So position vector 1, what's that? Yeah, so it's 0 I hat plus 0 j hat. That's easy enough. Position vector 2. And by the way, A, which is what they labeled as this distance. What was that, 10 centimeters? 0.1? Yeah. So A is 0.10 meters. So what's the position vector R2? Yeah. So in the picture, it would look like this. So here's R2, and that is 0 in the I hat and 0.1 meters in the j hat. And then what's position vector R3? Yep, and it looks like this. R3, 0.10, I hat and j hat. All right, so now we want to know force on guy on the corner, 3, due to both of the other charges, which means, well, how do we do that? I guess the first thing we should talk about is there are 2 other charges, so how do I find the force on the third charge due to both of them? What's the principle that we assume works? Yeah, we assume that you can, do the sum, the superposition of the forces, and that shouldn't surprise you in the sense that if this law tells you how only ever 2 things in the universe interact, what if you have 3 things? And the idea is, well, 3 things, well, there's pairs of interaction among the 3, and I guess the universe didn't have to be that way, such that they're additive, but it is. And so we never have to have a law that tells how 3 things actually interact. We just like, if I know how 2 interact, then 3 is just all the pairings that I can make in that mix. And of course, there is a pairing here we don't care about, in the solving of this problem. And which one is that? Yeah, we don't care about this pairing because it has nothing to do with the question, which was how is this guy affected by the presence of the other two. So obviously there's a pairing between 1 and 2, there's a pairing between 1 and 3, and there's a pairing between 2 and 3. And that's the only pairs that you can make out of 3 things. They asked us specifically, like, what's happening to this guy? So I'm concerned about 2, 3, and 1, 3, and I don't really care what these guys are doing to each other. Now, I would be concerned with that if somebody didn't take a nail and stick them in place or glue them down, because how these guys affect each other, if this was a dynamical process, is, well, they're going to start flying away and doing whatever they're going to do, and a lot of things would change. But the assumption is that they're fixed, and really that they're all fixed, because they're not asking about some simulation. And by the way, a 3-body dynamic simulation, not a fun process. That's like as simple as it ought to be. Simulation is your best friend if you try to do that. 3-body dynamical systems have never in history been worked out analytically, like on paper. We can't, I mean, that ought to make you pause for a moment and think like, wow, you like to pat ourselves on the back because we're like, look, we've not just made iPhones now, the iPhones can talk to us with artificial intelligence. Yeah, and wow, we have come a long way. And like, yeah, but this problem Newton was working on when he first invented the laws of dynamics, he was curious how the Earth, Sun, Moon dynamical system works out on paper. Can you do that for me? Like, no. Really? And it's strange. We can't. There's been some recent progress made by a team in Israel where they could place constraints on possible, in a 3-body gravitational problem, constraints on the possible behavior, but we still haven't worked it out. And maybe we never will, and that's disappointing. But if you took mechanics with me last semester, you also found out that we've never worked out in a closed form solution the dynamics of a pendulum either. And that's rather disappointing, equally, maybe more so. So anyway, we have to find 3, how this guy's affected, we have to really do 2 things. F3, 1, as in the effect on 3 due to the presence of 1, and the effect on 3 due to the presence of 2. This is what we need. We need to find that. So how do we do it? Well, we just do that. 2 terms. I guess I wish I had more real estate. All right, so let's do this. The F3, is this bad? Are you guys, that's going to be invisible, isn't it? Let's do it up higher. So with the little real estate I have, it's blocked out by all right, does that help a little bit? Can you see the bottom of the screen though, without my iPad in the way?
Yeah.
Okay. So F3, 1. How do I write it? Tell me what I'm plugging in if we're going to actually stick numbers in there. And we'll put the K in last, just because it'll make it yucky to do the math in our heads. So I'll put the K in as a K first. But then what numbers am I plugging in for the first 2 charge terms?
Should Q3 be the Q1 in the equation, and then Q1 be?
Yes. Yeah. So what he's saying is, since we're thinking of 3, 1, then every we're thinking 3, 1, 3, 1, 3, 1, 3, 1, right? So what does that mean here in terms of numbers that we have? I guess you can't tell in this case which one's which, but what are the numbers that we plug in if I'm doing the 5 microcoulombs, and that's really the charge on 3. Charge on 1 happens to be the same, so another 5 microcoulombs. And then what?
You have your R3 vector.
Yep.
R1 vector is 0.
Yeah, so I mean, if you take this vector minus that, how do we subtract vectors? Like, how do I subtract if I just gave you 2 vectors and you wanted to take R1 away from R3, how do you do that?
Just the individual components.
Yeah, you subtract. So to take R3 minus R1, and maybe I'll write, I don't know, we'll just say this is supposed to be the result of R3 minus R1. So the subtraction of vectors is done by the subtraction of the components. So this minus that, and of course minus 0 doesn't do anything. So this minus 0 and that minus 0 just leaves me this, right? So this is 0.10 meters I hat plus the same thing j hat. And then what do I do in the denominator? Yep, the magnitude of this thing, the difference, well, of course, that's the same as the magnitude of that. And so the magnitude of, how do I find the magnitude of a vector? Yeah, so I don't know if I left myself enough space. So the square root of first component, 0.10 meters squared, plus second component, same, oops, squared. And if this was a 3D vector, it's just one more squared term, but this isn't, so we don't care. That's the magnet, and so that's the square root of the sum of the squares. And then what do I do with that? And then I cube it, whatever that result is. So just realize the denominator, there is no longer an I hat or a j hat down here. There's no I here. So the denominator is a scalar. And plug it into your calculator and you'll get just a number. And you cube the number and you have the denominator. The direction part, the vector part, is retained in the I hat and the j hat, and then they come out of the numerator. So if we do this, I mean, an easy way, I mean, you can do it however you want, but by components, and maybe we'll do this. Could somebody work out this? Root 2, it's 0.14 meters, 141 meters cubed, and
0.002828.
so this term is 0.002828 meters cubed. All right. So if that's our denominator, then how do we get as, so what I'm wanting is I hat and then j hat. How am I going to get those components? How do we get the x component? And by the way, k is 4 pi times 10 to the minus 7 Newton meters squared per Coulomb squared. So we have a number. But how would I, given the value of k and given these guys and given the components and given the denominator, how do I get the first component? Just math-wise.
You just distribute it across the first term in the...
Yeah, exactly. So I would take, for the I hat component, I take k, obviously I can plug in the calculator that value, times this. What do I have to do with this so I don't mess something up? Is it just 5? Yeah, I do. I need to use coulombs as the base unit. So what's the micro prefix? Yeah, it is -6. So in my calculator, I'd be typing in 4 pi times 10 to the minus 7 times 5 times 10 to the minus 6 times another 5 times 10 to the minus 6 times a 0.1 divided by that number that was already worked out for us, the 002828. Can you guys do that and see what the number works out to be? So we have the x component.
That's 4 pi.
It is 4 pi. And that's, if you're wondering, like, really? Fundamental constant with a pi in it? This isn't a fundamental constant. Epsilon 0 that we'll talk about later is, and it doesn't have any pi's in it. But you getting? Anybody have a number yet? Hey, Google. What? Any numbers? 1.11 10 to the minus 15. Anybody get that? Good. All right. It's always bad when you get like 5 different answers. 10 to the negative 15, you said? Yes. 1, 5. What's the unit? Yeah, it's a force. It's going to be newtons. And of course, you got to work it out and make sure that that's right. What's the second term going to be? Yeah, it's not hard, right? Because, same here. If these were different values, the I hat and the J hat, it wouldn't be, but it is. So 1.11 times 10 to the minus 15 newtons. So look what happened. I have a vector. I don't have to guess what direction it is. I didn't have to work out its magnitude ahead of time. They wanted to know the force vector, so hey, look, I have that. And of course, we're not done because I have to do the other one the same way and then add them together. But this tells me the first part is the effect on this guy due to that guy is a vector, obviously, with a positive x and a positive y component. They're both equal, so it's pointing right along this direction. This is what we've just found. This is f on 3 due to 1. And obviously 45-degree angle because the components are equal. And then the other one we obviously have to work out is the F3-2, the effect on the corner charge due to the one sitting over here now. And so how's that? I mean, it's a very similar process, but what's going to change?
Just the 5.
Yeah, the 5 is going to change not just to a 2, but to a negative 2. And that's going to have the effect on flipping the signs of whatever components we end up getting out of the vector. So, but again, you don't have to manually work out what direction things are pushing and pulling. The math is going to do it so long as you put the sign in here. So this is going to become a negative 2 microcoulombs. And what's the difference vector going to, this part going to look like?
0.1 plus 0.
Yeah, so it's going to be 3 minus 2. So this minus that is still the same. So the first one is still a 0.1. This minus that obviously cancels, becomes a 0. And if the y component goes to 0, well, that's a force, and it's telling us it doesn't have a y component. And that immediately makes sense, doesn't it? Because what we're solving for now is what this guy feels due to that one. Better not have a y component, because it's got to be either pulled that way or pushed this way if there's another charge. And so all of the math just happens for you when you do that. Do we want to work that out or just assume that you could find x and a y of that just the exact same way that you did? And then what would we do once we had some number here? Once we figure out this and this, what do I have to do to finish this off? Since they want to know total force of that charge 3 is experiencing. Yeah, I'll just call it F3. Like, what is the force on charge 3 due to assuming everything? Just that plus that is the x component. So, hey, look, it's like, like that. This plus this would give you that, and this plus this would give you that, for the components. Does that make sense?
That gives you what?
The total force that so what these two individually are doing is saying, what is the force on 3 due to this one was the first one we did, and the second one would be what is the force on this guy due to that one, and the total force this experiences is, well, it's the sum of the two forces that it was experiencing due to the other two. And, so the process, and I think you can see, it's just so much easier than some manual process of let's first find the magnitude and then figure out which way I should point that force and make sure I get the angles right and do the trig and throw in a bunch of cosines. And we didn't have to touch a cosine or a sine. It's just, I highly encourage doing it this way because it's quicker and easier really to pull off, and you don't have to do any trig, you don't have to do any manual reasoning so that you could somehow mess things up in your head. You literally just run the math and you get the right answer. And it's not like we're going to be able to avoid trig everywhere and always, but insofar as we can, and you can just do things in a straightforward way and you don't have to intervene and try to figure out directions of things by yourself, I think you should just let the math do it for you. And this is the best way to do that. And ditto if this was a gravitational problem. So the only context where I think it's worth dealing with the inverse square version of this equation, which is usually written as, the force. If I get rid of that, then I don't have to worry about direction. So I just write KQ1 magnitude, because I'm not caring about the signs, over r squared and squared. And the understanding of this is, if I just want to know about how big is the force, it's worth remembering, as we showed that that's equivalent to last time, that it's an inverse square relationship. And in this context, this just relates to how far apart are charges 1 and 2. And of course, I don't care about the signs if I'm just caring about how big is the force, but you ought to remember that if they were opposite, they'd be pulling together, and if they were like signs, they'd be pushing apart. So this one, if it's just like, oh, super quick and dirty, and you just want to have a number for how big is this pull going to be or push going to be, great. But if you actually want to work out like some configuration of charges that you have, I think it's worth doing it differently. And there are some contexts where we'll do sort of an in-between, where we'll write an expression with a unit vector and kind of akin to that, but still looking at inverse square law. So you'll see variations of it, but I think it's worth seeing a diverse set of examples anyway. Yeah?
Is the 4 pi times 10 to the negative 7, is that supposed to be Coulomb's constant?
I don't think they give it a name. If they do, maybe they do. It's not a fundamental constant in nature, so.
Like in the Coulomb's law, like the K.
Yeah, I don't know. Does the book call it Coulomb's constant?
I think I read that. But it has like a different value in the textbook.
What did they give you?
Like 8.99 times.
No, that's epsilon 0, so which is a fundamental constant, and it goes in the denominator, 1 over 4 pi epsilon 0. You'll see that K, in order to make the gravitational equation look a lot like this, the gravitational one would have had a big G and a product of masses, and otherwise be exactly the same mathematical form. But K, by definition, is 1 over 4 pi epsilon 0. And this guy is a fundamental constant of nature, and that's the one that has that value of 8.85 10 to the minus 12. But obviously, if you do the math, it works out that if you want to write the equation with a constant in the numerator, then K, which isn't a fundamental because of that relationship, obviously they're not the same value, K and epsilon 0. Yeah, it would seem a little bit weird to take some non-fundamental quantity and give it a name as if it mattered. So does this make sense? Like, you can obviously, after class, compare this to what the book did, and I can't tell you what example number it'll be depending on the version of the text that you use. But if you find, with a Google search, the same version that I have here, you can compare them side by side and see how the math compares and how you'd work it out. Any questions on this? And yeah.
Is this the version you're going to be using for the homework problems? Or no?
Yeah, and by the way, just so you know, since some of you haven't had me previously, it would be a shame if physics, like learning of physics, resulted in you being basically able to mechanically do problems rather than understand what's going on and see something genuinely new and still know how to handle it. A big part of what I want you guys to be able to do is the kind of thing that we're doing on the board, but you'll see that we're soon going to be doing derivations and things of, given the distribution of charge in the shape of this, what's the field, the function that describes the field at this position in space. And some books will give you the idea that learning physics is all about, like, okay, so they did the derivation, here's the result, here's this equation, and I just need to plug numbers into that and get a result out. And that makes me want to cry, because the whole point is, like, how do we know that that's the case? And that requires the derivation to be the part that you know, to distinguish you from AI, as at least for the present era. The reasoning part, what are the fundamental principles? How do I take those fundamental principles coupled with math that I've been taught over the years and come up with the conclusions for all of those boxed equations that look themselves to be so important? You will not be having equation sheets of those boxed equations on exams. It'll be more like, okay, find the field. Starting from what? Starting from the few things that we will have memorized and doing math, which is what I try. This is sort of not even in itself a great example of it, but you'll see as we go by, it's more like proofs and derivations that I think is the only possible way for you to end this course with what feels like new knowledge. And I mean new knowledge in the sense of your picture of the world is different than it was when you came in, not I can crunch more equations than I could when I came in. You know, the purpose is you should see nature differently, not just imagine that, oh, if somebody gave me my equation sheet back, I could give you a number for the force. And like, who cares about the number of the force? Do you have a sense in which you see a wireless charger and you're like, I know how that functions. I could draw the fields and I could tell you what the principles are that allow me to wirelessly charge my iPhone in my car, or whatever the case may be. That's what this is about. It's some fundamental understanding. And like we were discussing last time, the calculations are easy to pull off. What trips up AI, at least presently, the most is like, well, how do you truly reason your way through a problem that's kind of complex and has many facets to it? And for the time being, that is still strictly a human property to be able to do that. But if you think doing physics is plug numbers into a given equation, well, you're already obsolete. There are much quicker ways to get that answer than to ask you to do it. And that also gives you no satisfaction when you're laying in bed at night and have your eyes closed and you're imagining something like your world is just as small as it was, because you don't even have your calculator with you. But if your principles and the concepts of the laws that run the world are suddenly like, oh my gosh, my world is so much bigger, now your imagination space is too, and hopefully it'll be a better place to exist inside your head. So that's what I'm going to try to push you guys to do, and hopefully it'll become an act of pleasure and not kind of horsewhip feeling. It takes some getting used to, I think, but and there was certainly a bit of that in 231 if you guys were with me, but it'll be more so because the math is beautiful in this course. The applications of vector calculus are endless, and it's nice, and it's really satisfying on the last lecture or two of class to see that literally 4 equations plus a little excerpt from, call it a 5th, really govern absolutely everything electromagnetic in nature. And we'll be taking only 2 of those to derive this stuff, like what is light mathematically, can we derive it? And we'll do that. And you know, those are the kinds of things that you really change your mind and like, wow, doing the math is powerful and interesting, not burdensome and why don't I get an equation sheet? So anyway, I'm going to try to sell that to you over the time that we have. How much time do we have today? 6 minutes. Why don't we talk about fields? Because I think that was the next thing in my list. Well, yeah, I don't think I have enough time to go into the symmetry discussion. So what do you get from reading about what is an electric field? They probably, I mean, for those of you who didn't read about thermodynamics anyway, what's an electric field based on reading? Yep.
A place where an electric force acts on a particle.
Yeah, and that was, I imagine, exactly the impression that almost everybody got from that, right? What we discussed last time is an operational definition. It isn't telling me what the field is, it's telling me what it does. How does it operate? It's saying, oh, it pushes and pulls on charges. And so they're saying, well, okay, and if there isn't this sense of being pushed or pulled on by a charge, then what's the conclusion? Put a charge here and it doesn't get pushed or pulled, what do I have to assume? Yeah, the field's, or that the field exists and is 0. So just so you have an understanding of the way physics really thinks of a field, is it's not something that you really add to space. You know, in the sense of like, oh, field is 0 here, and you're like, and now you change something and now it isn't. You're like, oh, what did I do? Did I sprinkle a field into the space-time? And the idea is that we are to think about these fields like properties of space, and space-time really. And you know, so that it is, and this is, you know, I mentioned last time how gravity is a little bit of an outlier, but all the fundamental fields in nature, you know, the gravitational, electromagnetic, the strong and the weak forces, everything that you've thought of as fundamental forces are mediated by fields. And the fields are not things added to space-time. The way to think about it is that space-time is such that it's natural for fields to exist in it. A property of a musical instrument is that it's made to resonate at certain pitches. And the string, you don't have to add a vibration to a piano string. It's the nature of a piano to have its strings vibrate and to have the soundboard resonate. And the way we should think about fields is that whatever space-time is, God designed it so that it is designed so that it automatically likes to create these resonances, which are fields. And we'll find, it's a little bit in this course, right at the very end, and much more so if you take modern physics, that absolutely everything in nature is a vibration of that field, which is not just the forces that mediate things, but everything that exists within them, us and fundamental particles. There is nothing else in nature besides wavy fields on the substrate that is space-time, the universe, however you want to describe it. So the universe is a realm in which only things that exist are vibrations, and those vibrations represent everything. The things, what we think of as particles, and the forces that mediate the behaviors between those particles. And I know the book doesn't go into that, but I think it's worth having that picture kind of as a starting point, because, so what we're really saying when the field is zero is, for whatever reason, nobody recently did anything. It's like nobody struck the piano string recently, so the string, while its nature is to vibrate, at the moment it isn't. But just like on a piano string, if you look closely enough, it is. Something's going to perturb it. And in the quantum realm, even if there's nothing around to produce an electric field, there are quantum fluctuations. Fields exist. And since the fields are equivalent to things in that picture, we should expect that in the middle of a vacuum, when nothing else is around and no energy's been added, that you might occasionally find things. And you do. And we can measure it. So occasionally, particle-antiparticle pairs come into existence in the middle of a vacuum of space with nothing else around, and then poof, they're gone. Just like you might expect tiny fluctuations in a piano string. And so it's a weird picture, but it's been verified better than any other scientific principle in the history of the world to precisions that would boggle your mind, and it's right. And so it's a weird picture. You are waves in a wavy world that contains nothing but waves. And the electric field is one form of a wave. Sometimes it looks like a standing field, but that's okay, because you can do that with the math. And sometimes it looks like traveling waves, which is, in the electromagnetic realm, exactly what light is. And like I said, at the very end of the course, we'll derive those waves mathematically. And it's pretty cool. Cool stuff. And a weird picture. But I've maintained for a lot of years that reality is way weirder than fiction. And throw AI into it, it's even more so. But I think we're out of time, aren't we? No, we have 2 minutes. Oh, it's beautiful. So that operational definition, I guess it'll be the last thing that I write here. They wrote this, F equals QE, in the text. That's half of the whole story. Later, we're going to add the second half to that equation. But for right now, what we're saying is that, in an operational sense, if there's some field that happens to be in space at this moment and you stick a charge there, which right now we're thinking of as particles, but they really aren't, then the thing feels a force and it moves. And of course, well, maybe it moves unless there's something else counteracting it. We weren't really asking in this question what's the dynamical consequence, but there's no question that if you didn't have glue or nails to hold these things down, this guy was going somewhere. And as it did, all the configuration would change, the vectors would all reconfigure, the calculation would have to be redone moment by moment, and that's a fantastic realm for simulation. Not so fun for humans calculating by hand, and impossible with a 3-body system to work out by hand. All right, have a great day. I didn't use this. Oh well. We'll get to that next time.